Hi, today we are going to see a topic in Unit 2 of Electric Circuit Analysis subject. So Unit 2 in Electric Circuit Analysis is network theorems. You'll be seeing about many theorems in this unit, and in this video we are going to see about Thevenin's theorem, which is one of the important theorem in this unit. So to see the statement about the Thevenin's theorem, it states that any linear active network with output terminals A and B as shown in figure A. So see this figure. Any linear active network, it can consist of any number of sources and any number of resistance, okay? That is a linear network with the terminals A and B to which the resistance RL is connected. So this network can be replaced by single voltage source VTH, which is called as Thevenin's voltage, in series with single impedance ZTH or RTH. So can you see here? This linear active network is now replaced by this single voltage source, Thevenin's voltage source, and this single resistance, that is Thevenin's resistance. So this is called to be as Thevenin's equivalent circuit, and this RL is connected here, and we need to find out this IL by using Thevenin's theorem. Okay. So steps to obtain Thevenin's equivalent circuit. Step 1. Remove the load resistor. First you must identify which is the load resistor and remove it and mark the terminals A and B. Step 2. Find VTH by applying KVL, that is Kirchhoff's voltage law. First find I, that is current for the loop, and then find the voltage. Okay. This you will understand it clearly while doing the problems. Step 3. Remove the source and find RTH. Suppose if it's a voltage source, if you remove it, you have to short circuit. Can you see it here? This is a voltage source. I have removed it, so it is a short circuit. And if it's going to be a current source, when you remove it, see it's a current source. If you remove it, it is an open circuit. Can you see the open circuit? Okay. So to find out this RTH, we can apply series and parallel logic and find the R equivalent, that is equivalent resistance, that is Thevenin's resistance. Step 4. Finally, find IL. IL, what is the formula? VTH, that is Thevenin's voltage divided by Thevenin's resistance plus load resistance. By using this formula, you can find IL, where RL is the resistor which we removed in the first step. Okay. Finally, we need to draw the Thevenin's equivalent circuit for the network which is given. So how will you draw? You have to find. You have to draw this voltage source, that is VTH. By applying KVL, you would have got an answer of VTH. No, write that and draw the source, and RTH you would have got in step 3. So that answer you write here and draw the resistors in series with this voltage source, and finally draw the load resistor and whatever value calculated for IL, write it here. So this is how you will finish with the step 5. Okay. So to make you understand clearly about this theorem, we can go and proceed with the problem. So problem number 1, determine the current I in the network by using Thevenin's theorem. So can you see this circuit? You have got 2 voltage sources, 3 resistors. Find the current I. So this is going to be IL current, the final current IL. Okay. So this current is flowing across 10 ohm resistor. So which is our RL? The 10 ohm resistor is our load resistor RL. Okay. This can be termed as IL also. Understood? So solution. Step 1, remove the load resistor. Okay. So we have removed the load resistor 10 ohms and mark the terminals A and B. Okay. Now can we go to step 2, find VTH by applying KVL. So where is our VTH? Between this terminal A and B only we have got our VTH, right? So you have to apply KVL to find this VTH. In order to find the VTH here, what current you must know? You must know the current I. So you must apply KVL for loop 1 first and find out the current I. Then go and apply KVL in loop 2 so that you will get the answer of VTH. So okay, see here, apply KVL to loop 1. What is it? 10. It is leaving at 10, right? So plus 10, and current I is flowing here from this source. So it is 4 into I, same direction. So minus 4I. This is then 6 ohms you have, right? So this is also you have got same direction, so minus 6I, and is leaving at minus, so minus 12 equal to 0. So once if you solve, you get the answer to be as minus 0.2. So you see I is equal to minus 0.2 amps. What is this minus sign indicates? Negative sign indicates current is flowing in the opposite direction, because always we'll take the current in clockwise and we'll proceed. And suppose if we get the answer in negative, it means that current is flowing in the opposite direction. Okay, opposite direction. That's all. So now after getting the answer of I, now apply KVL to loop 2. What is it? These two directions are opposite, right? So plus 6 into I, okay, 6 into I, because it's opposite we write it as plus, and this current is leaving at positive, so plus 12, and leaving at negative VTH, so it is minus VTH equal to 0. You know the answer of I, it is minus 0.2, substitute it and solve, you get the answer of VTH. So step 2 is over. Next we can move to step 3. So step 3 states that, step 3, what do you need to find out? To find RTH. So what you must do, you have to remove the sources. You had two sources here, both are voltage source. Once you remove, what you must do here, you have to short circuit it. So once you have done short circuit, what about these two resistors? It is connected in parallel. See, 4 and 6 are parallel. So by using the parallel formula, you get the answer of RTH to be as 2.4 ohms. So third step is over. Next, can we move to fourth step? To find IL. As I given already, the IL formula is VTH, RTH plus RL. You know this RL, right? This RL value which you removed in the first step, no? That 10 ohms. So add it here. You know VTH is 10.8, RTH is 2.4. Substitute, you get the answer of IL 0.871 amps. Over. Last, final step 5, Thevenin's equivalent circuit. So how will you draw? You have to draw the voltage source in series with the Thevenin's resistance and connect the load resistance. Write all the values. VTH is 10.8, RTH is 2.4, RL is 10, and IL which we have got here, that is 0.871 amps. So with this problem is over. So we have found this IL, that is our I current, which is asked in the question. Okay. Yes, to make you still more understand clearly about this Thevenin's equivalent circuit, in spite of following those steps, you can do it in different way also. So can you see this circuit? Yes, find Thevenin's equivalent for the network between A and B. In this circuit, you don't have any load resistor. Only A and B is marked. So the initial step, what you'll do? Solution, there is no RL. So take it to be as 0. So we need to find only VTH and RTH, and there is no RL here. So how to find VTH and RTH without following those steps? Already we know to do 5 steps. But here easily you can get this VTH and RTH by just using the method source transformation rule. Already in unit 1 or in starting of unit 2, you would have studied about this rule. If you have a voltage source in series with a resistor, you can convert that into, transform that into a current source in parallel with the resistor. How will you do? You know it is V into, so if you want the current, it is V by R. So it is 10 by 3, so 3.3 is the amps. So you draw the current source in parallel with the resistor. So this portion I have transformed into a current source along with a parallel resistor. And this portion can also be solved by source transformation again. So this is also a current source in parallel with the resistor. So you can change it into a voltage source in series with the resistor like this. So what is V? I into R. What is your I? 5 into 1. Then it is 5 volt. So since the arrow mark of the current source is in this direction, you have to put minus plus and draw it like this. Now can we redraw the circuit? See, I have redrawn the circuit here. This one and this portion I have redrawn. Now when you see this entire dotted lines portion, these two are both are current source, right? Both are in the same direction. So you can add. So once if you add, it is 8.33, and these two resistors you can solve by using parallel formula and get 1.2. See, and the remaining portion has to be kept same. Okay. Now what can you do with this portion again? This is again a current source in parallel with the resistor. So you can again do source transformation. You can apply the source transformation rule and change it into a voltage source in series with the resistor. So remaining portions you can draw it again. Now this dotted line portion indicates we can add. See, this is minus plus, this is also minus plus, so same. So you can add this two voltages. Okay, so both are leaving, if you take current, both are leaving at positive, no? So we can add this 2 voltage and make it as 15 volt. These two resistor, it is in series, so you can add and you can get 2.2, and this portion I have drawn it again. So now when you see, this dotted line portions, yeah, this entire thing, can you convert it again using source transformation rule? Yes, we can. This portion, if you do source transformation, you will get a current source in parallel with the resistor. Again, this portion, a current source in parallel with the resistor, you will get. So now you can add again these two current sources and get into a single current. These two resistors are in parallel and solve and gets into a single resistance. Now what you can do it again to get a Thevenin circuit, you convert this again by source transformation rule and change it into an voltage source in series with the resistance. That is 1.05, you have it here. And what will be your in order to get V, what is your formula? I into R. If you do, you get it as 1.911, which is our Thevenin's voltage, and this resistance will be our Thevenin's resistance. So this is how we have got our Thevenin's equivalent circuit in a different manner by just applying source transformation rule. So this is how you can do any problem which is being given. You can apply those 5 steps and get the answer, or you can just do the source transformation rule and you can solve and get the Thevenin's equivalent circuit. So by seeing this video, I hope you would have understood the Thevenin's theorem clearly. Thank you.